All right. Well, hello. Thank you, everybody, for making it to our second ever Lunch and Learn. My name is Ted Lucena. Most of you know me or have met me or asked for quotes on our website or have emailed me. We've probably spoken to each other maybe once or twice. But my name is Ted Lucena. I'm the sales account manager here at PME. If there's any needs regarding PME devices, new ones or new sales, please give me a call or send me an email. Without further ado, let me introduce to you Heidi Hirsh. I actually met Heidi, gosh, a few years ago, Heidi. I don't know if you remember this, but
it was a ways back.
We were at a couple of years. Ocean Sciences Conference had a meeting in San Diego. We're in Vista, California, which is a town just north of San Diego. It was right in our backyard. And I believe I met Heidi there. She mentioned that she used our devices, and she pointed me towards the poster session, and I checked out her poster. I think after that conference, I was just Googling around, found a paper that Heidi written, I think through Carrie Nichols, and Carrie reintroduced Heidi and myself. And yeah, so we've been trying to put these Lunch and Learns about once a quarter for everybody, just to highlight our customers' projects, our devices that they use within these projects. And without further ado, I'd like to introduce Heidi Hirsh to our second Lunch and Learn.
Thank you so much. Thanks, Ted. Like Ted said, I'm Heidi. I actually am in California now. I'm in Mountain View, California, just south of San Francisco. But I finished my PhD and I'm now working as a postdoctoral associate with NOAA's Cooperative Institute of Marine and Atmospheric Studies at the University of Miami. But my postdoc is entirely remote, which is why I'm on the West Coast. I'm now working mostly on coral reefs and carbonate chemistry related to ocean acidification in my postdoc, but today I'll be sharing some of my doctoral work from my PhD at Stanford University studying kelp forests. I studied kelp forests and seagrass beds, which I'll mention in a few slides. And I use a lot of PME instruments, especially in the kelp forest work, but in my seagrass work as well. So with that, I'll introduce you to this study and then dive into some of the details. So the title of my talk today is The Drivers of Biogeochemical Variability in a California Kelp Forest, Implications for Local Amelioration Against Ocean Acidification. And as Ted mentioned, this work was published in the Journal of Geophysical Research Oceans in 2020, and I've listed my other co-authors on the bottom of this slide. Before I move on, I just want to pause and let you know that it won't be like a typical talk. I'll do my data talk like I would in a conference or something, but I'm going to mix in pictures of instruments because I think that's what a lot of people are here for, is to hear about how I use these PME instruments. So in this photo, we have one of the mini dots to measure oxygen deployed on my mooring line, which we'll be seeing a lot more of. And that was my PhD involved a lot of this instrument intensive in situ measurements in these environments to address questions about ocean acidification. And so as a brief, just overview of ocean acidification. We know that carbon dioxide levels are increasing at a rate unprecedented in the last 55 million years of the geological record. This is a huge deal because atmospheric concentrations today are almost 50% higher than they were as pre-industrial concentrations. And so you can see in this plot our atmospheric concentrations in red. These are measured in Hawaii, and that our seawater concentrations of carbon dioxide increase with that atmospheric increase in CO2. And this is because as we have these higher atmospheric concentrations, it's driving an increase in seawater concentrations of CO2 as that equilibration occurs at the seawater surface. And this drives a series of chemical equilibria reactions, which ultimately lead to more free hydrogen in the ocean. And this increases the acidity of the ocean and decreases pH. So as pH becomes lower, that means that we have that higher acidity. And as pH decreases with this increasing carbon dioxide in the ocean, we also see this decrease in carbonate ion availability in the seawater. And this is because that carbonate ion is reacting with that free hydrogen. This means it's less available for calcium carbonate to be built into shells or skeletal material. So in your corals, in any kind of shellfish, crabs, a lot of these economically important species around the world are really impacted by ocean acidification, which is why I'm really interested in looking for local solutions or ways to protect against ocean acidification stress. And one of the solutions is looking at these highly productive marine environments like seagrass beds and kelp forests. So this was the focus of a lot of my doctoral work. And it's also something that managers and policymakers have recently embraced in this search for solutions. So they've embraced this idea that we might be able to find local or regional strategies to reduce stress exposure to ocean acidification, or to enhance the ability for organisms to endure acidification stress. And seagrass and kelp are two habitats that have been proposed as environments that may provide some protection against that stress. This report on the left was published in 2018 by the California Ocean Protection Council and California Ocean Science Trust, and it summarized some of the science at the time behind the capacity for seagrass and kelp in particular to ameliorate ocean acidification stress. So before I move on, I just want to show you a diagram from this report to introduce these habitats for those that don't work in them a lot or aren't super familiar. So a seagrass bed is shown here. Seagrass is a marine flowering plant. It has an extensive system of underground roots and rhizomes where it can store carbon for long periods of time. So in addition to taking carbon dioxide out of the water column, it's also able to store it for long periods. On the other hand, kelp forests, shown in this lower panel, kelp is a marine macroalgae. So it has an extensive vertical structure throughout the water column with a really dense canopy near the surface, but it doesn't have that root system. It anchors to the bottom using a holdfast. And so we don't expect to see carbon stored for long periods of time in this environment. But today I'll focus less on long-term carbon storage and transport and more on the short-term changes in the carbon system driven by metabolism in these habitats. And later I'll focus mostly on kelp. So this mechanism that we're really interested in is photosynthesis and respiration, or that primary productivity of these environments. Both are extremely productive. During photosynthesis, they remove carbon dioxide, which reacts with water to form a sugar and oxygen. So as photosynthesis continues during the day, we see that drawdown in carbon dioxide and an increase in pH or reduction in that acidity. And then we also see this increase in oxygen, which is why I'm really interested in measuring oxygen and pH as ways to monitor this reaction moving forward and monitor what's happening in these environments in the larger view of ocean acidification stress. So there are a lot of unknowns in these environments, especially in complex coastal areas like Monterey Bay, where this work took place, which I'll introduce in a few slides. But this was a diagram from that same report highlighting some of the knowledge gaps in kelp forest systems. And one of the biggest questions is, what is the transport between a kelp forest and the outside environment? So how extensive is that signal driven by that metabolism in reaching areas beyond the kelp forest? And then how do signals from outside the kelp forest impact what we are able to observe inside the kelp forest canopy? So I'm interested in deploying instruments to observe the signals in both of those areas. So the overall objective of my work was to determine the drivers of kelp forest biogeochemistry in order to better assess the potential for this kind of environment to ameliorate that ocean acidification stress on a local level. And to do that, I needed to identify patterns and drivers of variability in the system, both physical and biological drivers, where the kelp itself would be a biological driver, and ultimately get at this role for kelp to aid in ocean acidification amelioration or reduce some of that stress. Like I mentioned, this work took place in Monterey Bay at Hopkins Marine Station. Monterey Bay is located in central California, inside that dashed circle there. I'm actually sitting in my apartment very close to the upper part of that circle right now. That's where Mountain View is. And to put this work that I did in 2018 in the context of research that came before, these were 4 papers that were published that also looked at biogeochemistry biogeochemical variability in kelp forests in California. And of particular note is this Kowick et al. Study from 2017, where Dave Kowick and other authors deployed instruments actually in the same kelp forest where I did my work at Hopkins Marine Station. So in this kelp forest, I deployed 2 moorings, one inside the kelp canopy, where you can see the kelp in this satellite imagery. I'm actually currently continuing an effort to map these kelp forests with drones. I was supposed to be there yesterday, but it was too windy. So we have these maps monthly over the last several years as well. And then a mooring outside of the kelp forest. So here inside of the kelp forest, we deployed instruments to measure pH, oxygen, and temperature, which you can also see in this photograph. Every little bit of real estate on that mooring line was occupied by an instrument. And if I click, you can kind of see the lower part of this mooring, that's a mini dot there. And our other instruments extending up to a subsurface mooring buoy, which I've indicated here. I'll show a couple more videos in a moment. And at our outer mooring, we also deployed instruments for pH, oxygen, and temperature, but we didn't have the same degree of vertical resolution there just because it was deeper and we were more interested in getting that resolution inside the really dynamic kelp forest canopy. Since this is a talk about PME instruments, I want to focus on the mini dot for a minute. That is how we measured our oxygen concentrations as well as temperature measurements. And we deployed 3 of these loggers on each of our mooring lines. I've circled them in, or their locations in the yellow boxes here. And then these are a couple of photos of how those instruments were deployed on each line. We wrapped them in tape to protect from fouling, and then connected, or use a hose clamp to connect the instrument to the line, and then did like a little extra just in case connection with a zip tie through that hole at the top of the instrument. And to give you a better idea of the mooring locations, here at the bottom, we have a CFOX for oxygen and pH, and a mini dot here. This is pH measured with a mini FET, sorry, that's very loud. A thermistor for temperature, more pH, and you can see hose clamps holding on most of these instruments. Wait for another mini dot. There's another mini dot. You'll notice we deployed them upside down so that particles, which you can actually see here, weren't falling on the instruments. This work took place in the summer when there's a lot of primary productivity, so a lot of plankton and other kinds of biomass in the water that we didn't want to be building up on our sensors, although I will mention the mini wiper in a moment. There's our uppermost mini dot there, and a CFOX that also did pH and oxygen here at the top. I wasn't sure how that video would go through. I'm hoping it went through, but in case that was hard to see, here are some photos of the instruments on the line and labeled inside the kelp forest. So these are the lower 2 mini dots, and there were 3 total. So this is the same one as that. We have our mini dots on that line with our other instruments, and we also had the mini PAR deployed nearby, which I'll show you a better photo in a moment. More photos of mini dots. You'll all know what a mini dot looks like after this if you haven't used them. Again, these are our 3 that were deployed inside the kelp forest. So we have our uppermost one, that CFOX. When we deployed them with the mini FET, which is how we measured pH, we deployed it so that the sensor or the membrane on the mini dot was about at the same level as where the end of the DuraFET actually sticks out inside of this mini FET, so that we could get pH and oxygen at the same depth of the water column. And then again, we had that lowermost one deployed by the CFOX. Another video of our mooring line, a little bit clearer. Again, mini dot. And then this one I included because the end has our mini PAR. So that's the bottom of our mooring line. And then a few meters away, we deployed a mini PAR for our light availability on a cinder block. We also had a pressure sensor over here, which is inside that PVC pipe, but you can see the mini PAR. Well, you could kind of see it better here. The mini PAR deployed with that mini wiper to keep it from being fouled. So it was deployed facing up because it would be silly to deploy a light sensor facing down because we want to see that incoming light. And so we use those wipers to make sure that anything that fell on that would be cleared off. And we set the mini wiper to wipe every 6 hours. And the par logger was measuring every minute, and I think our mini dots were measuring every 5 minutes. And we deployed that mini par inside the kelp forest as well as outside of the kelp forest, both attached to these cinder blocks with, you can see like really large hose clamps to hold them on. And one more video, you might be sick of videos by now, but this one is fun, I promise. This started out as a video of the mini par and then our mooring line, and then gets interrupted by some charismatic megafauna. We all love charismatic megafauna. I love chemistry too, but I think everyone loves seals. So I thought I would include that. Okay, back to the data. So we have our 2 mooring lines inside the kelp forest, outside the kelp forest. The data that I'm going to show you today will focus mostly on the near shore and near surface and bottom data inside the kelp forest, and then our near surface measurements outside of the kelp forest. In addition to these mooring lines, we deployed acoustic Doppler current profilers to measure our current velocity at each of these sites. We also took surface samples, discrete seawater samples for carbonate chemistry with a small boat. And then we measured new frond growth inside of the kelp forest as a proxy for kelp productivity. And we measured chlorophyll A beyond the kelp forest as a proxy for phytoplankton productivity, because as I mentioned, there was a lot of phytoplankton in the summertime in this area. All right, so data. Before I show you the actual data here, I want to orient you to my color scale here. In this plot are shallower color or shallower deployments, so the data coming from instruments shallower in the water column will be in the warmer colors, and the cooler colors indicate deeper measurements. If I put up this data, this is almost 4 months of pH, oxygen, and temperature data from inside the kelp forest here. Those ticks on their x-axis are weeks. And you can see the oxygen and some of the temperature data is coming primarily from mini dots, and they were actually deployed earlier than some of our other sensors, which is why we have this extra month of data before our pH data starts there. You can see from this plot that we have multiple scales of variability inside the kelp forest. We have low frequency variability on the order of days to weeks, so these larger trends in all 3. And then we have higher frequency daily variability that is especially evident in these spikes. All 3 parameters were highly correlated, and we saw the lowest pH, so most acidic conditions, lowest oxygen, most hypoxic conditions, and lowest temperature, deepest in the water column, which makes sense. We can look at this high frequency variability in better detail by using frequency power spectra. So on this slide, I'll ultimately show you pH, oxygen, and temperature, but to orient you to this kind of data, I'm going to just show you oxygen first. So in this plot, the x-axis is our frequency in cycles per day, and these dashed lines I've added are at 1 cycle per day and 2 cycle per day, where you see these peaks in our spectral density. So if I bring in pH and pH and temperature in addition to the oxygen, you can see all 3 have these peaks in spectral density at those 2 frequencies. And what this shows us is the frequencies that are driving the most variance in our data. So there's something going on once a day and something going on twice a day. And if you think about it, that single once a day cycle is driven by our solar cycle, so by our light availability, as well as by our tidal cycling. And then that semi-diurnal, that twice a day signal, is further driven by our tidal cycles. And because these patterns are so similar across all 3 parameters, it suggests that there are common processes that are driving this high frequency variability for all 3. We also observed high frequency variability in our depth profiles of data. So here again, we're looking at data inside of the kelp forest. This is now 2 weeks of data where each of those ticks on the x-axis is a day. Our first panel here is upwelling favorable winds. Upwelling is a very common phenomenon in Monterey Bay, especially in the summer, where we have these upwelling favorable winds that drive this cool, nutrient-rich water that comes into the nearshore environment. So during these periods of high upwelling favorable winds, we see this delivery of that cold, acidic water. Again, here, kind of on this daily basis, if I had oxygen here, it would show a hypoxic signal, but we didn't have as good of resolution during this period. And then during the period of relaxation, when you don't have those winds, we see the water column warm and the pH get higher, so you have less acidity. And you see that there's especially high pH in the upper part of that water column, which makes sense if we have a lot of kelp there that could be driving photosynthesis, removing that carbon dioxide and boosting our local pH. We saw upwelling also impacting patterns on a low frequency scale. So we were looking at the high frequency daily patterns before, but if we look at a larger span of time, again, this is more on the order of, I think, 3 months or 3.5 months, we see this low frequency variability in those upwelling favorable winds. And if we pair that with our pH data, so here we're just looking at our near surface data and our near surface pH and bottom pH, you can see that typically if we have higher upwelling favorable winds, those are associated with our most acidic periods of time, our lowest pH. But looking at it this way, we only see a general relationship, and we can kind of do a qualified relationship, but to quantify it, we can use an index for our upwelling. And so here I've applied the beauty index, or biologically effective upwelling transport index, by Mike Jaycox. And if I plot that as these red points over time, that's our daily upwelling index. So better chance of upwelling when that index is high, versus our daily mean bottom pH in blue, we see that strong anti-correlation where our lowest pH again is associated with those highest potential for upwelling. And we can also view this by putting that index on our x-axis and our daily mean pH on the y-axis. Now we're looking at our near surface in orange and bottom pH in blue. That strong anti-correlation. Upwelling really drives this mean condition of pH. And the same is true for our mean conditions of oxygen and temperature. So upwelling is having a strong connection to those mean daily conditions inside of the kelp forest. Now that's a physical driver, but like I said, we have this canopy that has this strong productivity. We expect to also observe a biological signal in this chemistry data. So we can first look at that by, as we expect, primary productivity should drive this increase in oxygen during the day. So if we look at our oxygen here, and I've added a gray line for our oxygen saturation concentration as the backdrop, and then our near surface oxygen concentration inside of the kelp forest, those times when that concentration is above saturation are indicative that there's a biological process driving that elevation and keeping it elevated above that saturation concentration. So we expect something biologically to be happening during these peaks. And I mentioned that we did measure frond growth for a period. So if we add that data on this plot, we can see that the times when you have the most new fronds growing in the kelp forest seem to be associated with those higher oxygen concentrations. However, it's not that simple, because we also see very high oxygen concentrations outside of the kelp forest in their near surface. And they're actually higher than what we observe inside of the kelp forest, which is not explained by kelp growth, because if that was the case, we might expect to see some peaks outside the kelp forest, but we would expect them to be lower relatively to what we see inside the kelp forest. So if you remember my method slide, the other thing we measured is chlorophyll concentrations, which are a proxy for phytoplankton productivity. And if we add those chlorophyll concentrations here, we see that they're also associated with some of those higher oxygen concentrations, both inside and outside the kelp forest. So we can't directly relate what's driving the specific oxygen here, but it's very likely that we have a combination of kelp and phytoplankton production resulting in these patterns and the overall signal that we observe. On the previous slide, we saw those patterns in oxygen in the near surface inside and outside the kelp forest. Here, you can see that the patterns also hold up for our relative pH in the near surface, which is kind of weird that outside of the kelp forest, we would have higher pH than inside of the kelp forest because we have all that biomass. It's strange that pH and oxygen were higher, relatively higher outside than inside. But remember, this is a near surface measurement. So we're measuring a few meters down below that that canopy that we expect to be driving that signal. So it's actually not giving us that surface comparison. We can use the discrete data that I mentioned collecting from the little boat to look at the difference between surface pH inside the kelp and outside. And if we do that, if we take a delta of kelp minus outside in terms of pH, we see that typically we do have higher pH in the kelp at the surface relative to outside with a mean difference of 0.06. And then the other data we had at our disposal to look at the surface of the kelp forest, we deployed a mini dot for 2 weeks at the surface inside the kelp canopy, so on a buoy. And from our relationship for this 4 months between pH and oxygen, we were able to calculate pH from that oxygen concentration that we got from the mini dot. And from that, take a delta or a difference between our surface pH and near surface pH for that 2-week period inside the kelp forest, and see that there was a mean difference between surface and near surface of 0.05. So we do see this higher elevated pH at the surface of the canopy, but by the time we get slightly deeper, or by the time we move outside of the kelp canopy, that signal is already diluted or something. We don't observe that difference at that near surface that we would expect. It's already lost. So if we return to this figure that I showed you earlier showing data gaps, and now I've added a near surface section, since that's kind of the strength of a lot of my data, we can start filling some of these gaps. So we saw multiple scales of variability in this study. Again, those variability on the order of days to weeks, variability on hour scales. And we saw that the mean daily variability seemed to be driven predominantly by upwelling, so by our physical drivers, especially of that delivery of water into the deep part of the kelp forest. We also saw evidence, though, that the biology is affecting these chemical signals. So we saw evidence of phytoplankton and kelp productivity, both inside and outside of the kelp forest. Our strongest evidence for kelp modification, though, was at the very surface, where that canopy is the most dense. And that's interesting because our highest stress is likely at the bottom. If you recall my original time series data, the bottom is where we had our lowest pH, most acidic conditions, our lowest oxygen, most hypoxic conditions. So the greatest stress is going to be deeper in the water column, furthest away from that modification. And so this suggests that we have this spatial disconnect between our greatest stress exposure and the potential to reduce that stress at the surface. So at this particular kelp forest in Monterey, this suggests that organisms that can spend time in that canopy or limit themselves to the surface during stressful conditions are likely the best able to benefit from any amelioration that kelp forest is providing. So with that, that's the end of my data talk, but I added a couple slides just to show off some more instrument stuff from PME. I mentioned biofouling being an issue, which you can kind of see, oh, it's so loud, on this outer mooring. That mini dot there got all fuzzy. So to protect from that, we wrapped them in tape and that left them nice and clean afterwards. We also use these copper anti-fouling plates on the sensing end of the mini dots. So this is them in a tank afterwards. And you can see that for the most part, that kept those clear. But if we look at this one, where I've paired the instruments themselves with where they were deployed in the kelp forest and then outside the kelp forest, you can see that in some cases we did get some fouling on the membranes, but these were deployed for several months. I think we did one swap out, like one change where we had them out of the water for a couple of days and made sure that they were clean. And we may have been able to reduce that by using the screen anti-fouling, but we were a little nervous to do that in case something landed on it, grew, and then got stuck underneath. So it's kind of like, I don't know, figure out what your biggest problems are. And then the other thing, again, the tape, I just wanted to show some more examples of the fouling. This is mostly at the outside moorings. Inside the kelp forest, we didn't have nearly as much fouling on the outside of our instruments. And then I mentioned we used the mini wiper for the mini par. And you can see this is after a couple months out, this mini PAR was deployed, and it's very nice and clear from being wiped every 6 hours, but the wiper itself has been fouled. So you can tell that if we didn't have that wiper, that would probably be a problem. And I like this little sea star here. And then a final plug to my collaborator, Sarah Traeger. So my paper came out in 2020. Her paper came out just this last year from a follow-up study in 2019, where we actually did deploy instruments at the surface. And that was the biggest limitation in my study, is that we couldn't figure out how to deploy instruments safely at the surface inside of the kelp forest and beyond. And so for hers, we made this contraption with a float where we drilled a hole in the float to put a mini dot at the very surface, and it was held. I think I can again mute that. But if you watch that, you can kind of tell there's a hose clamp on either side of that float holding the mini dot in that hole, so that it's sensing right below the surface. And then we have the mini FET with that DuraFET inside to measure pH just a few inches lower. And so she was able to get surface pH and oxygen, which was very cool, and a very cool follow-up study. And that one is also freely available online. So with that, I'd like to thank all of my co-authors and funding from the National Science Foundation, as well as a lot of assistance from students in the field and from Hopkins Marine Station. Thank you for your attention. If you have any questions about the data or instruments or anything, I'm all ears.
Yeah, thank you, Heidi. Yeah, this will be the time for any questions. So if you would like to unmute yourself, and I don't know how we'll do this, but go ahead and just throw out your question, and Heidi can answer them for you.
Hi, Heidi. Great talk.
Thank you.
My name is Sam. I'm a staff researcher at Scripps Oceanography, and I also use mini dots for some long-term monitoring, but instead of in kelp forest, I'm doing nearshore environment underneath our pier. And I'm curious, this is some feedback I've gotten. You mentioned taking DIC samples for your pH measurements. Did you do any discrete sampling for oxygen calibration?
No, we didn't do any sampling for oxygen. We did calibrate. We did like the black bucket calibration with all of them, all the mini dots before and after, to make sure that they were all calibrated to each other and then to saturation concentrations. So we did do that. And then we also kind of calibrated them with our sea foxes. I worked extensively. If you're at Scripps, you probably know Yui.
Yes, I do. I work with Yui a lot.
Yeah, so like we did a lot of like calibration, kind of QC, like, do we trust this? And with that black bucket calibration, we were pretty confident with the oxygen measurements. But yeah, we didn't do any discrete measurements for oxygen or any like Winkler tests or anything. Okay. Which would be great if you have the ability to do that, because if you're at the pier, maybe that's something that's more reasonable. We weren't out often enough, I think, to where that would have been as useful.
Right. Yeah,
we didn't have a ton of DIC and alkalinity measurements to calibrate pH, but we had them like upon deployment and a few days after deployment. And then we were very close to Mbari, where Yui was, so we could do a lot of calibration tests and instrument work there.
Cool. Thank you for sharing that. That's really helpful. And we have hopes to expand our pH and oxygen monitoring to our local kelp forest and seagrass beds too. So this is really interesting for me.
Awesome. Yeah. If you have any questions, like logistical questions, feel free to email me too, because I feel like I've spent so much time doing QCing and like saving many different like documents and PowerPoints of like, what do we do in this condition? What do we do in this condition? And I'm happy to share any of that.
Awesome. Absolutely. Thank you.
Yeah, of course. Thanks. I think there's a hand.
Thanks, Sam.
That's me.
Fabian.
Hi, Heidi.
Nice to finally see you. Yeah.
Thank you for your talk. And yes, hi, Ted. Greetings from southern Chile. And down here, we are also have been doing some measurements with mini dots for the past few years, both down in the fjords of Patagonia and here in Concepcion, which is pretty much the same latitude as Monterey. So I wanted to ask you, I mean, I have some questions about the data, but I'll keep it to the how to deal with the mini dots when their sensor is covered in barnacles. How did you get them off, and did it affect your did your mini dots need to be sent back to PME after that?
No, I think they were okay. So I am not a biologist. I'm much more of a chemist. So I don't know what was actually growing on them. Like, I have a lot of pictures, but they kind of just like flaked right off. Like
they were barnacles.
Were they barnacles? Okay.
Yes.
Yeah, they weren't on there very strongly. So we were able to kind of like flick them off, for lack of a more, I don't know.
So it didn't damage the sensor?
No, yeah, the membrane was totally fine. The membranes are pretty sturdy. Like, I mean, I wouldn't scratch them on purpose, but for that we were like, okay, we don't want to put it in something that would damage it. So like, is it just going to come off a little bit? I think that was also at the very end. So I don't remember, because it was a few years ago, if we tried to take it off while it was wet or if we let it like die. We may have let it die and then it just came off better, because it was at the very end of the deployment when they were that fouled. And it wasn't an issue like a month in when we did our first swap. So it was only after a few months that we noticed the extra kind of fouling on there. But I definitely was nervous, and I was nervous about the data too at the end there, because I was like, okay, well, maybe this affected it, but it didn't seem like it did at all. And we luckily had the Endera optodes in the CFOX to compare to our oxygen measurements coming from the mini dots, and the variability and everything looked right in line with it. So it ended up being not as big of an issue as it looked like, but it was something that I wanted to share here just because we noticed that was something that happened, despite the like copper plates. And I'm not sure if it would have been better or worse to put the like screen on it as well. Because I wouldn't want it to grow too big pressure on it, you know?
Yeah, I was just going to bring that up, Fabian. We also have that option of the copper plate or the copper mesh. We could talk about that offline if you want to.
But anyway, barnacles managed to get through and settle where you don't want them to. And if you're replacing your mini dots every couple of months, you might have some trouble removing them. And we tried
it's tough
vinegar, for example, since it's calcium carbonate.
Because the copper kit, for everyone out there, we PME does sell a copper kit that comes with a copper mesh and a copper plate. And there's some positives and negatives to both. Obviously, when biofouling hits, the copper bounces off. But like Heidi and Fabian just mentioned, that there are possibilities that, you know, say you had the mesh, if the organism gets through at a microscopic level and then grows between the sensor and the mesh, then, you know, you might have some problems. What we found here at PME is using the wiper, which Heidi showed some pictures of her mini par with the wiper, and the wiper comes with a copper plate. So again, when biofouling hits the copper, it bounces off. But with Heidi's wiper, they're wiping every 6 hours, I believe she said. So whatever lands on the non-copper portion, which would be the sensing foil, the wiper will wipe what's left over there. And that's probably the best method, but it's also the most expensive method that we have here. But we are running a sale for everyone out there. If you guys buy the wiper and the logger together, just give me a call or send me an email.
Ted, or anyone else on this call who uses mini dots, have you used or seen the mini wipers used on mooring lines? Because that was like, it was very easy to deploy a mini dot on mooring lines. You just clamp it on. And I know the wiper had like the frame for it has, yeah, exactly. But it'd be harder since it's a plate to attach as well, I think. I don't know. I'm sure it would work. Also 6 wipers, yeah.
Yeah.
We're not in the budget, I don't think, at the time. But I think that is a good solution for preventing fouling, because it certainly prevented it for the mini par.
Yeah,
Yeah,
I
we
mean,
have
and the way
used that.
you deploy them on your mooring line, there are holes on each of the wipers and the casing of the logger, as well as the bracket. So you've got some places to work with.
Yeah.
And yeah, we just probably use zip ties maybe through the holes and then onto the mooring line.
Those clamp it around.
That'll probably be your best bet.
Or thicker line, or just attach it to the other instruments too. Although then if you lose one, you lose 2, which was our nervousness about the surface originally, because there's so much traffic outside of the kelp forest, and then, you know, otters and critters inside the kelp forest or at the surface, where we were nervous about things. And we did have one, the mini dot was fine, but we had a mini fet that for pH that got hit by somebody's prop on an outer line in the 2019 study, just because it got tangled by something going by. So like the surface is still a risky place to put instruments, but it really paid off in terms of data, because like I suspected from my data, the surface was where things were going on, and we saw that signal more prominently in Sarah Traeger's paper. But yeah, deploying upside down too, I think reduced the amount of stuff that we got on our sensors, but it was definitely an issue for bubbles. So on that
I was just going to bring
oil
that up.
membrane,
Yeah.
the bubbles built up. And so when we were QCing, we luckily thought to look for it. So we'd mark down when we dove on our mooring lines, because the bubbles are, of course, we're diving on the mooring lines. So there's a lot of bubbles coming up on there. But the thing we didn't think about was like other people diving in this area, like students and classes going out. And so it was hard to get records of, okay, was someone else near the mooring line causing bubbles, or did we have some weird spike? Which we were able to use when we knew that we had divers on the line to kind of characterize like, okay, that looks like divers creating bubbles on our oxygen sensors, and cut the data that way. And I have a lot of examples
Heidi,
of that.
Yeah, you actually had a really good picture. For all those out there that haven't deployed mini dots on a mooring line, she didn't have them up, you know, that would cause more biofouling. She didn't have them completely down because she just mentioned the bubbles. She had them out just kind of slightly to avoid both the bubbles and the biofouling. So that's how you want to deploy them on that mooring line.
And you can do that by like if you hose clamp the middle and then like zip tie that top part tighter, it flips out. Yeah, flips the side out a little bit. But we also just like swished under it going up the line, and that seemed to reduce it. I don't know if you give me screen access, I can show you the bubbles. I think you're sharing a screen maybe right now, Ted or somebody. Yeah, that looks like. Or if there are other questions too. Figured I do have examples.
I'm having some trouble. But yeah, we'll have this. Well, we have recorded the presentation, so everybody could come back and check out the slides and, you know, check it out. But does anyone else have questions for Heidi? I know we don't want to take too much of everybody's time. I know everybody's busy, but we'll take maybe 1 or 2 more questions and wrap it up. Looks like we're wrapping it up. So I want to thank everyone for coming out and checking out our Lunch and Learn. I want to thank Heidi for her presentation and showing us her project and her using our devices here at PME. And without further ado, just feel free to give us a call or send us an email, sales@pme.com or info@pme.com, and If you need to get in contact with Heidi, if that's okay with Heidi, I'll help with the contact information as well. I'll be your go-to guy for that.
Absolutely. If anyone has any questions about like our logistics and setting up these mooring lines, or questions about the research too. And like I said, both those publications, I think were linked in the invitation that Brenda sent out for this event. But contact me and I can give you access to them as well. Thank you so much.
Sounds good. Thanks everyone for showing up. Thank you, Heidi, and we'll see everyone soon. Take care.